Well, hello again. In this example, you will see the method of virtual work being used to solve for the deflection of certain locations within a truss. We will take a look at this particular truss that has certain properties. You can see the dimensions there. Reactions are already found. The applied loads are properly identified. Even the orientation of the members have been identified as well. Virtual work requires us to analyze the forces in this truss. This truss is known as the truss that has the real loads on it. And so we're not going to run through the analysis of the joint by joint, but you will have to do that on your own. We're going to note that this is a symmetric structure, and if I do joint analysis, these are the values that I'm going to gain through the analysis of the applied loads as they currently show. 810 pounds, 540 pounds, 810. The positive means it's tension in all of these. This is negative 905.6. Remember, AB is the same. Negative 754.7 and 243.4. Remember, BF and DG has a force of negative 243.4. So you'll notice some of those are in tension, some of those are in compression. Once again, symmetry was used, so I'm not going to label every one of the members here, but what we've labeled will suffice. Another piece of information that the virtual work method is going to require of us is to know the length of our members. So member BF here, we can use just a little bit of geometry to get this. L is equal to 64.9 inches. Of course, down here, the length of these segments is 144 inches. The length of these upper chords, L is equal to 120.7 inches. And within here, the length of CG and also CF is equal to 129.8 inches. We want to be consistent in the units that we use for our analysis, so we recognize that E is 1900 KSI. Since I'm going to be working in pounds, we'll call that 1,900,000 pounds per square inch. And then let's note that all of our members have a cross-sectional area of 5.25 inches squared. Recall that the virtual work method for calculating deflections is of this basic form that says the virtual load 1 multiplied by delta, the desired deflection that we're trying to find, can be computed by taking a summation of the bar forces due to the virtual load, little n, times the bar forces due to the real load, big N, times the length of the member, all divided by its cross-sectional area, and modulus of elasticity. Currently, we have this quantity, this quantity, this quantity, and this quantity. So the last thing we need to get is the forces in the truss bars due to the virtual load. So we will place a virtual load, let's call this the virtual structure here. We will place a virtual load wherever we want to know the deflection. So notice here it's at point C. Now why at point C? Because the problem statement asked us to find the vertical deflection at joint C. So we place a unit load and we then proceed with the analysis. It may be very helpful for you to recognize when doing these types of things that identifying zero force members becomes very, very helpful. So for example, look at joint B. The three members come together at a joint, but two of them are collinear. That means member AB and BC, those are collinear. Then out of necessity, the third one must be a zero force member. So likewise, this one would be as well. Mentally remove those members, and you will notice that bar FC also meets that same requirement. So we have identified these four zero force members. Now we can carry out the basic analysis from here. So this comes out to be negative 1.12. And we just do this using the method of joints. And the bottom chords come out to be a positive 1.0. Okay, so we've got the real structure analyzed, we've got the virtual structure analyzed, and we now need to put all that information into a single table. And that's what we have going on here. I'm going to remind you once again that virtual work says that the vertical deflection at CY is equal to that sum of little n, big N, L over AE. Now in this particular example, AE is constant. So I'm actually not going to put that in my table itself. You could if you wanted to, and that wouldn't be a problem, but I'm going to handle that later. As long as it's constant, I can do that. So within my table, I want to make sure that I've identified the appropriate units that I am using for each of these. Keeping in mind, then in the last column here, I'm computing little n times big N times L. And so I've got that for each of the individual members. Then what I can do is I can sum up that column. And that's where I get this right here, 759932. To finish out the computation, say 1 times delta CY is equal to the summation of the NNL, so that is 759932, and that would be pound inches, all divided by 1,900,000 psi, that's my E, and 5.25 inches squared, that's my area, and that will compute out to be 0.0762, and the units on that will be inches. Now one thing I want you to notice is that comes out to be a positive value, and the only thing that a positive value means is that I had assumed the correct direction. And how did I assume direction? It was the direction that I applied for my virtual load. So I applied that in the downward direction. Since my value came out positive, that means I did indeed deflect in the downward direction. This particular problem is asking me also to look at the horizontal deflection at joint E. And so I place a virtual load out here at joint E. For this particular structure, identifying zero force members will save you a lot of time. Zero force, then I can determine that these are zero force, and then I determine that these are zero force, and that makes these zero force. And so all I have here are these members right here that have any kind of force within them. Once I've got that, I can put that in the table. I want you to just recognize here that only 3 members have a virtual load that is non-zero. Let's go ahead and sum up once again this little n, big N, L. That comes up with this quantity. We can put that in our virtual work equation. 1 times delta EX is 311,040 pound inches divided by 1,900,000 pounds per square inch times 5.25 inches squared. This will come up to be 0.031 inches. It comes out to be positive, which means I did assume the correct direction, so I'm going to give an interpretation arrow here. And that is the method of virtual work as it applies to trusses. That concludes this example. As always, it's a beautiful day to study structures.